All right, hello everyone. My name is Brian. I am the Department Chair of Mathematics and Statistics at Okanagan College. And in the last video, we took a look at what the Euler Phi function does for us and how it counts the number of co-prime integers less than n, positive integers less than n. And we took a look at how to prove some of the basic fundamental building blocks for how we do the calculations. So what I want to do in this video is look at some of the properties of the Euler Phi function. Some of them are really interesting, and some of them have some really cool connections back to modular arithmetic that we were working on in some of our previous videos as well. Some of the properties we probably will utilize in some upcoming videos when we're working with some algorithms, specifically probably Fermat's little theorem and Euler's theorem are in here, which I think are, if I remember correctly, important key pieces in like the RSA algorithm, or some of those more advanced like cryptography algorithms. So let's start with the first property of the Euler Phi function. So if I have a couple of, let's call these positive integers. So let's make sure they're, in the set of positive counting numbers. And let's say we know that the GCD of m and n is 1. So these are co-prime numbers. Then if I'm working in the following way, like I know that I can take this number that I'm inputting into the Euler Phi and I can break it up into two co-prime integers, then I can really just break this up and say, okay, well, this should really just be phi of m times phi of n. So this maybe allows me to take a larger number, break it down into co-prime components, and work with those components. And this is often easier to do. It's always easier, in my opinion, when because with cryptography algorithms, we're often working with these really, really massively large numbers. So any way that we can convert those numbers down into smaller numbers to work with is always super advantageous. So, I mean, we're going to work with numbers that are relatively easy to put into our calculator just as we start to learn some of the fundamentals. But some of these algorithms use prime numbers that are like thousands of digits long. So it's kind of impractical to ask a computer, okay, what's phi of this ridiculously large number? It's easier for us to maybe test some prime numbers, try to break that down into smaller pieces, and then start factoring or start breaking down that number into prime components, and then it's easier to work with functions like the Euler Phi function. So that's kind of the background stuff that's happening in some of these algorithms. For now, we're going to focus on taking a look at some smaller examples. And let's connect this one explicitly back to the last example that we just saw. So let's look at phi of 702. So the way that we did it was we said, 702 was 2 times 3 to the 3 times, 13? And so way one, we just straight up said phi of 702 is equal to 702 times 1 minus a half times 1 minus a third times 1 minus a 13th. So this was just a straight up way using prime power factorization, and we ended up with the number 216. Now, if we were a little bit lazy and we didn't necessarily want to go all the way, drill down all the way, and find these explicit prime numbers, what we could do is we could find numbers that are co-prime. So let's say, for example, I just happen to know that 702 was equal to 27 times 26. I mean, not most people wouldn't know this, but let's just say. So what I'm doing effectively is I'm taking this 3 to the power of 3, which is my 27, and 2 times 13, that gives me this 26. The property says that since these two numbers are co-prime, that I really should be able to think about this as phi of 27 and phi of 26. So I should be able to break apart the Euler Phi function in this multiplicative kind of way. And then we might convince ourselves, okay, well, 27 is 3 cubed. There's only one prime here. 26 is relatively straightforward to factor as well. It has factors of 2 and 13. Therefore, I can rewrite this as 27 times 1 minus a third. Right, that's phi of 27. And then I can write this one as 26 times 1 minus a half and 1 minus 1/13. Okay, so I can break these apart individually like this. And notice, too, that I am capturing what I originally had, right? I can see these three factors that I had originally. Like, they're still there. And this 27 times 26, well, that's really 702. Right? So as long as I'm looking at co-prime factors, when I continue down the line, I recapture all of the factors that I need to get that 216. Now, we can look at this in an incorrect way as well and ask ourselves, okay, why is co-prime important to being able to utilize this forward process? We could try doing something like this. We could try saying, well, 702 is, I don't know, 9 times some stuff. It would be 9 times 26 times 3, which is 78. But now the problem is these are not co-prime anymore. So let's see how this breaks down. So notice here that the GCD of 9 and 78 is 3. Is 78... It's not divisible by 9, right? It's just 3. So the GCD here is 3. So this part here is the incorrect part, just so you know. This is the incorrect part, but we're just gonna see what goes wrong. So if I try to utilize this procedure that we just saw, we would get something like, okay, well, now I know 9 only has 3's in it, 1 minus a third. 78 has a factor of 2, a factor of 3, and a factor of 13. Right, so 78 is 2 times 3 times 13, right? And so what happened? Well, we ended up double counting something. So in our original case up here, there was only one, we only needed one copy of the 1 minus 1/3. Down here, because the GCD is 3, we actually double copy that factor of 3. So this is why it's important to have the GCD of 1. So GCD of 1 just ensures that we don't double copy or like double multiply one of these factors and end up with some incorrect output. Okay. So property number 2. Property number 2 is phi of n to the power of k is equal to n to the k minus 1 phi n. That's kind of a cool property. Is this one easy to prove? The last one wasn't. It's easy to prove, but it just takes really long to prove, so I kind of skipped it. Yeah, that makes sense. Yeah, okay, that's cool. Okay, this one's actually not too hard to justify with a proof, so let's go ahead and prove this one. Like I said, the first one is doable, it just takes a little bit of time and effort. Okay, so let's take a look at how we might think about this. So I'm going to think about this in the following way. I know there's a formula, and the formula basically says it doesn't really matter what this number is. I just take this number, and I need to multiply by 1 minus 1 over all of the prime numbers. So I'm just going to assume here that I have like m of these prime numbers. All right, so these are all of the prime numbers that are important. I can probably just do a dot, dot, dot here. So dot, 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 1 minus 1 over p to the m. So let's say P1, P2, Pm, and everything in between. Those are the important prime numbers for this number n to the k. Now, I'm going to take this n to the k, and I'm going to do something like this. I'm going to break this up into n to the k minus 1 times n. And then all I need to do now is to convince myself that this is really just phi n. And I can see that, right? Like, if P1 to Pm are the prime numbers for n to the power of k, those are also going to be the prime numbers that are important for n. So yeah, all of this is really just phi to the n. So there you go. There's a little bit of a shortcut way. If you notice that you have a kind of perfect square, perfect cube number, or really any power, we can simplify by kind of pulling out that n to the k minus 1, and then that lets us focus on the smaller number inside of the Euler Phi function. Yeah, the P1 to the Pm are prime numbers, yeah. So here are P1 up to Pm are the prime numbers that we find in the prime power decomposition. So it looks like a lot of blah, blah, blah. So let's take a look at an example. So what if we wanted to calculate phi of 132 to the power of 5? Well, the property above says, okay, I have this to the power of 5. I need to actually do 132 to the 5 minus 1. And then I need to find phi of 132. So that's what the theorem up top says, or the property up top says. Now, 132, I can go about doing that a couple different ways. Maybe the easiest is to just see how we might take 132 and find its decomposition into prime powers. Is it divisible by 4? It's divisible by 4. That's going to be 25 and 8, which is 32. Is this 32 and 4? That doesn't seem right. $33. Okay, that feels better. Okay, 33 and 4, so that's a 2 and a 2, and over here I have a 3 and an 11. So 2, 3, and 11 are going to be the important pieces that we need in order to calculate phi of 132. So we do 132 to the 4, and then we multiply that by 132 times 1 minus a half, 1 minus a third, and 1 minus 11th. So basically we get 132 to the power of 5 times a half times 2 thirds times 10 elevenths. And then I'll do maybe some... It's not really super easy to do some of this, but we'll get rid of those at least, and then we'll multiply out the rest and see if our calculator can handle this number. It's probably too big for our calculator. But we'll see anyway. So 132 to the 5 times 10 divided by 3 divided by 11. It's too big for a calculator. I mean, we'll throw it in here. 132. Does it? I wonder if it'll do that. No, it doesn't. It doesn't recognize it. So even this one can't really recognize it. So I might just leave this in factored form. Right, 132 to the power of 5 is pretty big. So, but this is what we're looking for: 132 to the 5 times 10 over 11. I could probably get rid of that 11 if I wanted to. What's 132 divided by 11? 12. So 132 to the 4 times 12 times 10 is what we're looking for. All right, so whatever that number ends up being is going to be the number of co-prime numbers to 132 to the power of 5. Right, so it provides us at least a way to kind of move forward and get a reasonable idea of how many of these things are going to be co-prime with that starting number. Okay, property 3 is a little bit of a weird one. It says if we have a divisor then there's this like really weird relationship where I can take n and I can rewrite it as phi of divisor 1 plus phi of divisor 2 all the way up to phi of that last divisor. So that's a little bit weird. And this one is a little bit tricky to prove too. We have to kind of think about fractions and how fraction relationships work. So I'm going to kind of skip over the proof of this one, but you can take a look in your textbook if you want to better understand how to prove that one. But let's take a look at an illustrative example. I'm going to take a look at 12, and I'm going to calculate all of the divisors of 12. So 12 has the following divisors: 1, 2, 3, 4, 6, and 12. So in order for us to verify this equality, we're going to have to find the Euler Phi function for all of these divisors. So we know phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, because 3 is a prime number. Phi of 4 is just 1 and 3, so 2. Phi of 6 is 1 and 5, so also 2. And then phi of 12, what's that going to be? That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'd be 4. So this theorem says if we look at 12, we should be able to actually break it up in the following way. Which I think is kind of weird. But it does show you a little bit of the beauty of this mathematics, right? It's sometimes quite surprising in a direction that you wouldn't really expect. So is that true? Is 12 1 plus 1 plus 2 plus 2 plus 2 plus 4? Yeah, 6 plus 6, right? Checks out. And like I said, it has something to do. You can kind of prove this using fractions and adding up fractions to make sure that things work out properly. But I don't think it's important for what we need to do in our course. So read about it if you're curious about it. Otherwise, I'm not going to spend more time on the proof. But it is a really interesting property, I think, of the Euler Phi function. Now, we're coming up to the two big boys for this particular lesson. We have Euler's theorem and then Fermat's little theorem. So these are the two big theorems that I would say connect back to what we were looking at before, which is working in the mod arithmetic kind of realm. So what does Euler's theorem say? Euler's theorem says if n is a positive integer, and I have GCD of n and a is equal to 1. Here a is any, let's just take any positive integer. So maybe we'll call this z plus. So if I have a positive integer and I grab another positive integer that's co-prime with n, then a to the phi n is congruent to 1 mod n. So this is kind of an interesting theorem, and I want to give an illustrative example before I do the proof. And it has, I think, some very similar strategies to what we were doing before, like looking at, certain sets of numbers, multiplying them, and then trying to reconstruct some of the stuff that we're looking at here. And it will rely a little bit on the group structure of modular arithmetic as well. So before we do that proof, let's take a look at the following illustrative example, and I'll really try to break this down. So let's take n is equal to 9, and a is equal to 2. Now we can just kind of blindly check that this is the case if we want. So if we take 2 and we raise it to the power of phi of 9, so phi of 9 is everything that's less than 9 and co-prime with 9. So 1, 2, 3, 4, 5, 6, 7, 8. So there should be 6 integers less than 9 that are co-prime with 9. So if I go 2 to the power of 6, I get 64. And Euler's theorem says this number 64 should be congruent to 1 mod 9. And I can see that that's the case, right? The closest I can get up to when thinking about division by 9 is 63, and I'm going to have 1 left over. Now, why is this important? It's important because now we have a number, this number 2 to the 6. I know that it should have an inverse, likely have an inverse mod 9, right? So that's kind of an important bit of information here, right? If I can find two numbers that multiply together that give me 1 mod 9, I know that those two numbers are inverses of each other in this modular arithmetic realm that I'm working with. So I think that's probably going to be the importance that we use a little bit later. But for now, I can kind of go through the motions of doing this. I can see that it works, but why does it work? Why is this always going to be the case? So let's kind of dive into this a little bit more. So the first thing I want to consider here is let's consider phi of 9 and try to figure out what those elements look like. So let's take phi 9. We know that that's 6, and the elements that we're working with are as follows. What do we have? We have 1, 2. We do not take 3 because 3 is not co-prime with 9. We can take 4. We can take 5. We cannot take 6. We can take 7, and we can take 8. So those are our 6 elements that are co-prime with the number 9. Now it turns out that these elements form a group under multiplication mod 9. Okay, so in other words, what does that mean? That means that we have closure under, what do we need? Inverses and multiplication. So it's closed under multiplication of elements, and it's closed under taking inverses. So what we're saying here is it's closed under multiplication. So if I multiply any two of these elements, it's going to stay inside of this set. 1 is going to be our identity element under multiplication, so 1 times any one of these things would be itself. And then all of these numbers also have inverses, which is potentially interesting, but maybe not unobvious if you know a little bit more about groups, which I don't know how familiar you all are with groups. But notice here A We've basically identified A, I think, as the the cyclic element that's going to generate this group, right? Like 2, 2 squared, 2 cubed, 2 to the 4 is 16. That's going to be 7 mod 9, and then 2 to the 5 is 32, which should be our 5 mod 9, right? So 2 ends up being the generator of this cyclic group. For those of you that know that terminology, so everything is going to have an inverse here because it's a nice kind of closed loop cyclic group here that has a generator. Okay, so I think that's kind of like we have a bunch of elements. These elements form a really interesting mathematical structure that's called a group under multiplication mod 9. And 2 is invertible, so that's another important thing here. So the element 2 is invertible mod 9, and we can verify this. So 2, we know 2 to the 6 is congruent to 1 mod 9 based on the theory. So this would imply that 2 times 2 to the 5 mod is congruent to 1 mod 9. Or 2 times, what did we say? 2 to the 5 is 32. And if I divide by 9, the closest I can get is 27. So that's going to give me the element 5. So 2 inverse it is 5. So 2 and 5 share this interesting property that if I multiply them together, I get 10. That's congruent to 1 mod 9. So these two numbers are inverses of each other in this mod 9 kind of world. So there's a really cool property that says since 2 is invertible, then I can take this list of values and I can multiply or scale them all up by 2. And I'm going to capture all of the congruence classes again. So we talked a little bit about congruence classes last time. We would have, in this case, 6 different possibilities for congruence classes, mod 9. We have 1, 2, 4, 5, 7, and 8 are going to be the natural choice for the equivalence classes under this particular relationship. But if I multiply by 2, I also get an equivalent set of congruence classes that would cover all of the elements that I need to cover as well. So this is a property of inverses when we're working in multiplication modulo arithmetic. We should be able to look at this set. So let's take our original set, multiply everything by 2. And we would say that by scaling up by 2 here, we get another set of congruence classes, mod 9, that would do the same work as what we had before. So this is another, we used a particular phrase for this. I just want to make sure I get the correct phrase. I think it was in this part here. Okay, we talked about relations. We talked about mod as an equivalence relation. We talked about congruence classes. And we talked about a complete set of congruence classes. So that's kind of what we get here. So this is a complete set. Now remember, we're working in multiplication mod 9 here, not addition mod 9. But this complete set here should be equivalent to the set that we have up here of 1, 2, 4, 5, 7, and 8. So if this is another complete set of congruence classes, then that gives us the following. So we could say that if we take 2 times 1, and we multiply that by 2 times 2, and multiply that by 2 times 4, etc. So multiplying all of these numbers together should be congruent to multiplying the candidates of our original congruence classes together, which would be 1, 2, 4, 5, 7, and 8. This should be true in the mod 9 multiplication world. Now, we are allowed to do associativity and commutativity here. So I'm just going to pull out all of these extra factors of 2 and rewrite them as 2 to the 6. And then I have 1 times 2 times 4 times 5 times 7 times 8. All right, this is congruent to our 1 times 2 times 4 times 5 times 7 times 8, mod 9. And we know that each one of these elements has an inverse, so we can multiply by the inverse elements here to basically get what we want. So we will multiply by the inverse of all the elements we need to. That's going to give us 2 to the 6 congruent to 1 mod 9. So hopefully that gives you like a little bit of the kind of structural backbone as to why this is going to work. We can check that it works just by doing the computation. That is true. But there's kind of this underpinning mathematical structure called a group that's doing the work for us. So we have this group structure. In this particular case, we had a nice cyclic structure of that group. We had an invertible element, so we were basically able to scale everything up by that invertible element, ensure that all of these have kind of a one-to-one mapping with the original complete set of congruence classes, and then simplification gives us the result that we want for this particular example. So that's kind of the basic idea. Again, I'm not sure if the proof is like super helpful to go through, but that's the idea, right? You kind of have your set of original complete congruence classes. You now have your invertible element, which we're calling A in this particular case. Multiply everything by A to get a new set of congruence classes that is also a complete set. And then you can go through this process of kind of factoring out A. You end up getting phi n copies of A because we're in a group under multiplication mod n. So we only want the coprime elements to ensure that they have inverses, basically, right? And you end up getting this really, really cool property called Euler's theorem. Okay, and there's one corollary that I just want to finish off with that is a spur from Euler's theorem, and that's going to be Fermat's little theorem. So this is called Fermat's So remember, corollary here just means that it's usually a result of the previous thing that we discussed. So Fermat's little theorem says the following: if n is prime, and we pick some other a, so we have the GCD of P and A is 1, so here A is any maybe positive integer, because that's what we've been talking about so far. Then we have A to the P minus 1 is congruent to 1 mod P, not mop P, mod P. So if we believe Euler's theorem to be true, basically we're saying, okay, well, if we have a prime number, n is just prime, so 1 mod p makes sense. phi of p is really p minus 1. That's the formula we have. So this is why we call it a corollary. So if we know that everything is true, we just kind of replace n with a prime number, then we should get this relationship instead. So let's take a look. I'm not going to prove that one. I think it's hopefully clear once you kind of see how Euler's theorem is phrased, and then we're just substituting n equals p in there to get the result that we're looking for. So I have an example in here. I don't know exactly how we're going to do this, but it says evaluate 2 to how many zeros is this? 1, 2, 3, 4, 5. So this is the 100,000 mod 77. Okay. So we must have to use one of these theorems. I notice, I'm just kind of talking through without looking at my notes, but I noticed that 77 is 7 times 11, and the base 2 is co-prime with 77. So I do notice that right away, so I'm just going to write that down. I do notice that the GCD of 77 and 2 is 1. So I don't know if I can use Fermat's little theorem because I don't have a prime modulo, but I might be able to use Euler's theorem, which says if A and N are co-prime, then A to a particular power is going to be congruent to 1. So the power that I'm looking for is phi 77 is what I'm kind of curious about. So maybe that's what I'll do first. Is maybe I'll take a look at what is phi 77, and I'm looking at that because I know that 2 to the phi 77 should be congruent to 1 mod 77, right? This is Euler's theorem. So let's take a look at this. So phi of 77, there's only 2 prime numbers in here. So I need 77, 1 minus a 7th, and then 1 minus an 11th. So we get 77 times 6 sevenths times 10 11ths. So we should get 60. So we know phi of 77 is 60. So what we could do is we could figure out how many times does 60 go into 100,000. That's going to be the next question. So 100,000, let's divide that by 60. So we're going to get am I doing this right? Yeah, I think we basically just want to block off a bunch of 60s, right? So 1,666. So if I take 100,000 and I subtract 60 times 1,666, I'll be left over with 40. So I think I can reduce this down to 2 to the 40. By doing something like this. So let's see if I am doing this properly. So I'm going to say that this is equivalent to 2 to the 60. And I'm going to raise that to the 1666. And then I need to multiply this by 2 to the 40. So let's see if that makes sense. We know, based on our exponentiation rules, that this should be 60 times 1,666 plus 40. And we know that's equal to 100,000. Okay, so I think I did this properly. That is a hell of a lot of 2's. That's a lot of 2's. Okay, so I'm comfortable with that. That makes, actually, maybe I'll leave that in there in case you guys want that as a reference. So I think I'm okay with that. And so now I can say that this is congruent to 1 to the 1666 times 2 to the 40 mod 77. Right, this is Euler's theorem. So Euler's theorem says 2 to the power of 60 should be a congruent to 1. So all of that first little bit's going to go away, and I'm going to be left with 2 to the 40 mod 77. Okay, that's still a lot of 2's, though. So what do we do with the... But, I mean, it should now hopefully be... I mean, this is still pretty big to do division by 77. So can we break this up into things that are easier to work with? So, I mean, my calculator can't probably calculate 2 to the 40, right? Not easily. So I still need to break this down into something that's easier to work with.
He roped me into this. Well, that one over there roped me
Hi,
into
Sai.
this.
Congratulations on your third. So what if we did like 2 to the 10? I'm looking for something that I can actually like write out. So yeah, we might be able to do 2 to the 4 copies of 2 to the 10. So let's think about that. So this is 2 to the 10 to the 4 mod 77. So that's 1024 to the 4 mod 77. So how many times does 77 go into 1024? 13 times. So let's go 1024. Let's remove 13 copies of 77. And we have a remainder of 23. So we can reduce this to 23 to the 4 mod 77. We're getting there. Does my calculator like 23 to the 4 is the next question. I have a feeling that's going to be pretty big. It's pretty big, but it's manageable on my calculator now, right? So 23 to the 4 I have. I can now divide this by 77, and I get 3634. So let's take 23 to the 4, and let's subtract off 3634 copies of 77. That's, oh shoot, that's all in the numerator, or in the exponent. 3634 copies of 77. And that's going to leave us with 23. What the heck? That's fun. Anyway, sorry, I was just thinking that's kind of interesting. So this should be congruent to 23 mod 77. It's kind of weird that 23 to the 4 came out to be congruent to 23. I would have expected that maybe it would get transferred to a different number. Okay, so... Oh, cool. Okay, so that's great. That's exactly kind of roughly how I solved it in my notes, too, so that makes me very happy. Very happy man. Yeah, I definitely cannot do that. I definitely cannot do 23 to the power of 4 in my head. That's not happening. But, I mean, I guess the flow of what we want to do is we want to take this outrageous number, right? Like, we're taking an outrageous number. We're trying to utilize Euler's theorem to get rid of a lot of those things. 2 to the 40 was still pretty big, so we broke it down into a number that was more manageable to do at our calculator, and just kind of kept breaking it down further and further into stuff that we were able to do on our calculator to get to a final answer here. So that's really all that I would like to do for today. So that should finish up your video lessons on modular arithmetic and the Euler Phi function, and hopefully give you a pretty nice kind of fundamental view on how some of these background structures work for number theory.